Now, when we look at a reaction coordinate diagram or an energy diagram, we should be able to identify some sort of structures. So with the transition state idea, this is based on the assumption that we can generalize the structure of the transition state depending on whether a reaction is exothermic or endothermic. If we have an exothermic reaction, the transition state is closer in energy to the reactants. And so therefore, the transition state, it actually mirrors the state of the reactant. So whatever the shape of the reactants is, technically we can start to think about the behavior of that transition state to be close to the reactants. And the same is true for an endothermic step or process. The transition state is closer in energy to the products, so we should be able to look at the products and identify something about the transition state based off of that. When we get into actual reactions in Chapter 7, this will become a little bit more apparent. But what this means is in an exothermic reaction, reactant stability is very important to understand the transition state stability. In an endothermic process, the products are important for their stability to understand the stability of the transition state. Nucleophiles and electrophiles. This is where we're starting to dive into brand new territory. For a reaction, polar reactions, we are going to see ions as reactants, intermediates, or products, right? Negative charges are attracted to positive charges. Opposites attract, we know that. But we also know that electron-rich species mean that they have a lot of electron density. We want to relate those to negatively charged items, right? It could just be a delta minus or an actual minus. It might be a lone pair. It could be a bunch of different things. But we want to start thinking about, does the atom have a lot of electrons? Or is the atom deficient in electrons? Are they more positively looking? And so when we look at this carbon atom, that's what we're focused on right here, is the carbon in these two molecules. When carbon is bonded to chlorine, carbon is electron deficient because the polar bond between carbon and chlorine is pulling the electron density towards the chlorine. So carbon is feeling electron deficient, looking more positive, not an actual positive charge, but a delta positive. When carbon is bonded to lithium, lithium being a metal, then we start seeing that lithium pushes its electron density towards carbon, making it electron rich, having more electron density closer to the negative charged species, because lithium will take on the delta positive, carbon, more electronegative than lithium, takes on the delta negative. So in a reaction, we have to be able to start to label electron-rich species and electron-deficient species. A nucleophile, nucleus loving from the Greek. Nucleophile means that it is an electron-rich species that is looking for a nucleus to pair with and to love and cherish. So nucleus loving, what's in the nucleus? Protons. Electrons attract to those protons. So a nucleus loving species must have a lot of electrons to donate. That lithium to carbon molecule has carbon being the actual nucleophile. We can think about lone pairs and a negative charge. Oxygen in this ethoxide ion is the nucleus. Even without a lone pair, or without a negative charge, lone pairs are still considered nucleophiles. We will also see pi bonds, the electrons in the double bond or triple bond. Draw a triple bond on here too, just so I'm not discriminating against our pi bonds. Those will also be nucleophiles. Now, the more polarizable the nucleophile, the stronger it is. And so we'll be able to talk about what that means in just a little bit. An electrophile is the electron deficient species, electrophile, so electron loving, something that's looking for electrons, is going to accept a pair of electrons. So these are going to look like more like acids, whereas the nucleophiles look like bases. The electrophiles look like acids. The most, though the easiest one to think about is the carbocation. Remember that carbocation is an empty p orbital, and that's what gives it the formal charge of +1. We can also see polar bonds when they again give carbon a delta plus charge. So there's the electrophile, there's our electrophile. Carbocations and partial positive atoms are electrophiles. Typical ones that we will see: delta negatives, lone pairs, pi bonds, those are all nucleophiles. They're electrons that are ready to go out and attack a nucleus. Electrophiles are our delta pluses or our empty p orbitals, and those are the ones that we are going to focus on. Curved arrow mechanisms. Now, we already kind of did this in acid-base reactions. When a base meets an acid, the base lone pairs will go pick up the hydrogen and kick off a minus so that we make BH, the conjugate acid, and A minus, the conjugate base. Now, with these curved arrows, this is an acid-base reaction, or what we are going to call a proton transfer. But again, it's starting with something that is electron rich, the base, going towards something that is electron deficient, which is the delta plus on the proton. So we already do know one type of ways that polar reactions show curved arrows and mechanisms. It's a proton transfer. We're going to go through all of these. A nucleophilic attack, we're going to see a loss of a leaving group, we'll see proton transfer again, and then we'll talk about rearrangements. And all of these curved arrows or mechanisms are used to show how the electrons move as bonds are breaking and forming. For a nucleophilic attack, a couple of things that we can see. Essentially, what we're going to be looking for is a nucleophile attacking an electrophile. That's the main goal of a nucleophilic attack. Bromine has the electron, so I'll highlight those a little bit bigger. There's my nucleophile, and it's attacking, pointing right to the electrophile. There is one way to do a nucleophilic attack. You could have an ion, right? That's a good way to identify a nucleophile. Doesn't mean it's a great nucleophile, it just means that it is going to be deemed the nucleophile, and arrows usually start there. Another way that we can look at a nucleophilic attack is attacking a pi bond. We'll see this one a lot next semester. Nucleophile, again, got some lone pairs. It can attack an electron deficient center because of a polar bond. Now that carbon is the electrophile, but that carbon already has 4 bonds. So what has to happen is a pi bond can break and roll up onto the oxygen. We'll practice these a lot, so don't worry about them too much right now. It's just being able to identify, can I see what type of bond I have? Or what type of curved arrow am I forming? Excellent. Nucleophilic attack can also be a pi bond. I have one more to show you with this. Again, this will be next semester. But with those aromatic compounds, they're some of my favorite. You might have a nucleophilic attack where the pi bond breaks, attacks a center, and which pi bond do you kick off? Well, you only need to kick off one, and it doesn't matter which one you kick off if you have multiple and they're all going to the same atom. But what's really important to note is that those formal charges, right? So note where the atom is going, how many things are on those atoms, and make sure that the formal charges of the reactants and the products are equal. Excellent. Only one carbon atom from the pi bond uses the pair of electrons. So notice here, carbon number 1, carbon number 2. Only one carbon can collect that new bond. The other one will get a positive charge when a pi bond will react as a nucleophile. There again, there's the nuke. And that sulfur is the electrophile. We'll get to all of these reactions. What's important to just note right now is, again, the process, right? The definition. Loss of a leaving group. We're just going to do a very similar one to what we did before. We could have a bond simply break. That's the loss of a leaving group. Bromine is leaving. The heterolytic bond cleavage of an atom where it takes the electron pair away from whoever it was bonded to. Right? There's our loss of leaving group. Bromine is the leaving group right there, or bromide is the leaving group. We could also think of a leaving group having more than just that one arrow, but we'll stick to just the one arrow right now. Proton transfers. Proton transfers happen readily between acids and bases. We can look at an acid and base and call it more specifically a nucleophile attacking an electrophile. But when that nucleophile attacks a proton that is an electrophile, that specifically is a proton transfer. So this could look also like a nucleophilic attack. However, the nucleophile is specifically attacking a proton, so it's a proton transfer. Nice. Rearrangements. Carbocations can be stabilized by neighboring groups. The orbital overlap that's happening here with a carbocation is called hyperconjugation, very similar to our staggered formation, why staggered was more stable than eclipsed. So looking at this methyl group, when you have a carbocation, it's an empty p orbital, and it actually can be stabilized by a sigma bond right here. The sigma bond that is filled can start to hyperconjugate and donate some electron density towards the carbocation. That is stabilizing, just like the hyperconjugation was before for our staggered Newman projections. So the more carbon groups you have around a carbocation, the more stable it is. Methyls, where there's no carbon groups, a methyl carbocation is the least stable carbocation. Will not form, ever. Don't even try, it's not going to show up. Primaries, sometimes written as primary carbocation by myself, those are not super stable. They're more stable than methyl. Right here is a big dividing line of what we typically see. Secondary carbocations can form. There's enough hyperconjugation with two R groups donating electron density towards the carbocation. Tertiaries are the most stable of our R group systems. Allylic, we've seen these before, resonance stabilized carbocations are the best. So if you have resonance right next to that carbocation, these are even better than tertiary. The increasing substitution increases the stability of the carbocation, and that is just due to the increasing number of adjacent sigma bonds that can align with that empty p orbital and hyperconjugate. So with rearrangements, what we want to be able to look at is there are two types. The first one is called a 1,2 hydride shift, and it will happen when there is a carbocation adjacent to a more substituted carbon and has a hydrogen to move. So here we have a secondary carbocation. It's a carbon with 1, 2 R groups, right? So it's a secondary carbocation. Next door, there's a tertiary carbon, a carbon with 3 R groups. The hydrogen on that tertiary carbon will shift. I'm going to draw in that hydrogen over here just so that we can see it move. And what happens is that hydrogen picks up the electrons as a hydride, H minus, and plops itself down on the neighboring carbon, the carbocation. The reason for that is because when it does that, we create a tertiary carbocation, one that is more stable. The only time this will happen, the only time rearrangements ever happen, is when a carbocation is secondary and can become tertiary or primary even. We can sometimes see an intra type of a rearrangement. It's going to be super fun. We'll get there. But overarching idea, something is going to become more stable. A carbocation is going to become better. A 1,2 methyl shift can happen as well. Hydrides and methyls can shift. Nothing else can shift because nothing else is small enough. So if you have, again, a secondary carbocation, and say you have a quaternary next door, one that is a carbon with 4 carbon groups, a methyl can shift over. Notice the origin of that arrow is from the bond. That bond can shift over a methyl group. And again, the carbocation becomes more stable. We'll practice these a lot in class. I made this diagram. I think it's important to be able to know these heterolytic reaction types. Please don't try to memorize them, but definitely look and find the pattern of them. I think that would be extremely important for us in drawing curved arrows, in making sure that we don't have any issues. The octet rule is important to remember, so we'll be practicing that a lot. And I will see you all in class. Thank you so much.